is canceled. And so now Ruben Rosales from MIT is going to give a talk on very different things. Something different from what we talked about this morning.
Right.
Okay.
Okay. So I can use this and feel like a singer, right? Okay. So I know, but this makes you feel like you're a singer. No, I'm just joking. So is it true that I have 2 hours, so I can have an interruption of 5 minutes and then just go on for 2 talks, right? I have plenty of slides, so I can just talk for 2 or 3 hours anytime you want. Okay, so first thing, so Paul proposed for the ways forward the title of Fluid Dynamics is Going Wild. That was supposed to be the sub-theme that he said, and this has been an emerging sub-theme in this conference in the last couple of days, so I decided to change the title to that, just to fit better. All right? So now I'm connecting up with gas dynamics, relativity, black holes, everything. All right? I'm not going to talk about 1/3, though. All right. So what I want to talk about is this. There are things that are observed in traffic flow, which are sort of traffic jams that arise out of nowhere, and they're called what are they called? The phantom jams. Okay. And so what I'm going to show is that these phantom jams are in some models of traffic flow. They are related to they are similar to detonation waves in gas dynamics, and they are related to an instability that arises. And that instability is in turn related to the existence of event horizons in the traffic flow. Okay, and all right, so this is okay. I'm not going to go through the outline. What the heck? You'll see what I do when I do it. Okay, so this is an example. It is a movie taken by Helvin in Cairo, and okay. So watch what happens, all right? Okay, so look around there. See that thing there? And then another one there. And if you wait one, they're going to start drifting backwards. And so you see, okay? And this thing is forming out of nowhere. There's no accident or anything like that. These things just form. And then there was another one there, and another one there, okay? Sometimes it's the same one. Yeah, there's one going through and there are new ones that show up. All right? The point is that...
But how do you know nothing happens? There's an entrance around there.
Okay. So, all right. The point is, I'm going to show you... Yes, somebody sneezed. The point is, in traffic flow there are no experiments, except that sometimes there are experiments. I want to show you the only experiment in traffic flow I actually know. Huh?
Is this real time or no?
This is accelerated. No. They drive pretty fast, but no, this has been speed up. I don't know. I didn't take the movie, so I have no idea. Okay, so, all right. So, okay, this is the next one. This is an experiment. This was done in Japan. Okay, so here we have a loop traffic flow. So they took 22 cars, they put them around in a circular road.
How did they make it there?
Okay, guys, this is turning into... And these guys were told to drive around the circle at I think it was, I forgot the velocity, something like 35 kilometers per hour.
In 2014, you can do this experiment around Maracanã, the stadium.
Good. I'll ask for funding from NSF to do that. And so they were told to drive around at a constant velocity, keeping a constant distance from the next car. And... okay. So this is what happens. All right, so I don't know why the guys didn't get 22 equal cars. They're all different. But if you watch this thing, you're going to see what happens. So there, okay? Okay? So right. So you get the same thing, okay? All right. So these things have been known for a while. So let me now, I claim these things are detonation waves. Okay? So basically the statement is that, you have these homogeneous conditions in traffic flow, And you get these instabilities, and the thing becomes inhomogeneous, even if there are no obstacles, no bottlenecks, or anything like that that's visible. Okay. Now, of course, you have drivers which are not perfect. Okay, but actually, there has been experiment done with robots. Okay, and they get the same thing. All right, they put the robots in a truck, and there's a little computer chip that's supposed to look at the next guy and keep the distance fixed and so on, and you get the same problem. All right, so it's really not something completely directly related to human beings. Okay, so all right, so these are I'm going to describe first the kind of traffic models that people use. There are basically 4 types of traffic flow models. First, you have cellular automata, and those are kind of very complicated. Lots of parameters in them. So you can fit what happens in a road with this one by choosing the parameters properly. And this is the things that people sometimes use when they try to do some kind of engineering traffic calculation. They are very hard to understand as to what is happening. Okay. Second kind of traffic flow model, this is one of the oldest types. This is relatively new. This is one of the oldest types, and this is just, you model the cars by an ODE. Every car is characterized by its position in time, and then you write some bunch of ODEs where, each car looks at the next one and figures out what to do on the basis of that. All right? So you end up with a...
Is that the same mule of lepton and port thing?
No, look at this date. It's a different one. Okay? No, this new one, this is a new one. A different one. All right, then there are these so-called mesoscopic things. They model them by sort of Boltzmann's equations. The problem is this involves a sort of a collision term between cars, and it's not clear what the hell that means. And finally, you have these macroscopic continuous models, which started with Lighthill and Witham in 55, and there's a whole bunch of them. And they're not very accurate. Okay, you get the description of traffic flow similar to the dog that Nathan pictured, okay? But they're much easier to understand. All right, so let me quickly describe the macroscopic ones. If you in a single lane, you simply assume that there's a corridor on the road. Forget about this periodic thing, but that was motivated by the picture of the Japanese cars going around the round. There's some car density, which is just rho, and then flow velocity. And, you assume you can sort of like look at them on a large scale enough that you can think of them as continuous variables. Then you end up with a continuity equation that's just a conservation of cars. And then you need one extra equation to complete the system. The simplest possible thing you can do is just say that the drivers, there's a relationship between the velocity at which people drive and the distance to the next car, which is preferred, and that gives you some relationship between the velocity and the density. You plug it in there, now you get a model for a single equation model for traffic flow. These are the so-called first-order models. You can do something a little bit more fancy, which is to say that, okay, there's some law, something that describes how the cars accelerate. And, so you make this some function of rho and u, and then you end up with a system of 2 equations. All right? So these are the so-called second-order models, and there are various types. So I'm going to tell you a little bit about these ones. So, okay. Somehow there is something fishy. The thing doesn't fit on the screen. All right, never mind. Okay, so first of all, the simplest kind of the form it has to have, if you think about this, basically it has to be maximum when the density is the smallest, say 0, and it goes to some kind of it goes to 0, some critical density where the cars are so close together that it will just stop. All right, and so the simplest thing to say is just a straight line. So that would be that one. Okay, and of course it's not a straight line, but that's more or less what it looks like. And people have measured this thing, and it's reasonably close to a straight line. Okay, so then if you do that, you get this stuff. So now you get the Scalar Conservation Law. It turns out that if you look at this equation, it's generally nonlinear, so it develops wave breaking. If you now postulate that the wave breaking is resolved by shocks, which conserve density, you get this thing with shocks. And if you look at the shocks, which sort of correspond to this rapid transition between densities, they more or less do the correct thing, which is to say they move backwards to the traffic. Okay, like if when you drive, you never have a traffic jam catching you from behind. You always drive into it. And these models have that property. They also have the property that you leave a traffic jam slowly, you get into the jam, and you're stuck from there, and you slowly accelerate and get on the other side. Again, this kind of property is built into this model, but it doesn't have this sort of spontaneous instability of homogeneous traffic. You don't get the phantom jams. All right? To get the phantom jams, you have to go a bit farther, and so the simplest second-order model is this one here, in which you forget about this term for a moment. Okay? You assume that the cars accelerates towards the desired velocity with some time lag tau. Okay? By the way, that time lag tau is not the human response time. That's the inertia in the cars. All right? This is in the order of 4 or 5 seconds. It's not half a second. Okay? So the dominant effect is not the human reaction time. It's the fact that you have these massive things that take a while to accelerate. All right. Now, if you just do this model and scratch this thing, that actually is an ill-posed model. I mean, the solutions just are a disaster, right? And basically, the statement is if the drivers really drive that way, the ill-posedness means you get collisions all the time. And the reason that's not what drivers do, they also they're aware of the traffic variations, and they don't blindly accelerate to the velocity that just the distance to the next car would determine. They actually sort of have some idea of the gradients. And so if ahead of them the traffic density is going up, they will be accelerated a little bit less. And if, on the other hand, the density ahead of the next car is going down, they will move a little bit faster. It's kind of like you see that when the light goes green, people start inching forwards even before the car ahead of them moves. Okay? So, or they start braking before they have to brake. So that's modeled by this term, this P, which sort of acts like a pressure. Think of it as this thing actually, essentially, what it does, it modifies this velocity by something which is proportional to the gradient of the velocity. Oh, sorry, the gradient of the density. So if you have an increase in density ahead of you, namely rho x is positive, then you accelerate to a lower velocity. And if you have a decrease in density below you, you accelerate a bit more. All right?
Px or rho x?
Well, P is a function of rho, so this becomes some constant times rho x. Okay.
You said it was ill-posed without that?
Without this thing it's a very bad problem. It's just horrible. It's actually ill-posed. You know, you get arbitrary large growth rates for short waves. Okay. All right. So this thing is important. You can't not have it. Okay. And so this is a way to model that. All right. And so when you model this, so these two things are called as prevented driving and optimal desired velocity. So in all the continuous models have these two things. There's some way of modeling prevented driving, and some way of modeling the idea that there is some preferred, distance between cars that's related to the velocity at which you are. This particular choice here, that's the Pine-Witten model. All right? And so if you write it down completely, it looks like this. All right? So if you look at the left-hand side, it very much looks like the equations of gas dynamics. All right? With in the case of the polytropic gas. All right? And now the question, of course, what are you going to choose for P? All right? Now, while this guy is very easy to figure out roughly what it should look like, this one is a bit harder. What you really know about this one is that it should become, it should be something that becomes stronger as the density goes up, all right? Because the denser the traffic flow, the more, cautious the drivers are going to be. Okay, and so a very simple thing by analogy with gas dynamics that people do is something like this, all right? But this is bad. And the reason this is actually bad is that, in fact, when you reach the jamming density, you become infinitely cautious, and you really just stop driving, okay? And this doesn't do it. So if you want to model that, you have to put a singularity in the P. And so you have to write something like this. This one would actually really, stop the density from overshooting above jamming. which this one allows. Further, of course, it's a hell of a lot harder to analyze models like this than this one. Okay? So this guy is the worst part of the model. It's not clear what the hell to choose there. All right? All right. So the point is that these equations are hyperbolic and generally nonlinear. And that means they generate shocks. Okay? So in addition to the Pine-Witten, there are various other alternatives. There's a model proposed by Ruben Rosales in 2000. There's another more general model proposed by Helbig in 2008. These things model preventive driving in slightly different forms, and the justifications for them have to do with, different ways of thinking of how preventive driving happens and trying to resolve difficulties of the models. In any event, what I'm going to talk about now is common to all these models. They all have this phenomenon, all right? So another problem that all of this model has is the following thing. So you have this wave breaking. You need to put shocks. Shocks are observed in the sense that you do see these rapid transitions in traffic flow. But in order to put shocks in the second-order model, you need two conservation laws. One is obvious, conservation of cars. What is the other thing that's conserved? Well, it's not clear. All right? I could just go back to this thing here and say, well, actually this thing conserves momentum. So I'm going to put conservation of momentum. But the truth is, you're braking when you're in a shock. So how the hell could you be conserving momentum? All right? It's even worse with the other models because they don't even have a physical quantity that's conserved. Like the Ruben Rosales model has some thing that's conserved, which is very strange. And when you impose conservation of that, you actually find that the cars are accelerating across the shock, which is completely insane. But in any event, that is unknown. All right? This is an open problem. It's not clear what shocks lock to use. So what I'm going to do now is I'm going to show you some numerical calculations. I'm simply going to just do them with conservation of momentum, just to have some law. But basically, again, what I'm going to describe, the only thing you actually need is to have some shock law that satisfies reasonable criteria for shocks, which means you need the information to go into the shock and die there. In other words, they have to satisfy the lax entropy conditions. And as long as they're satisfied, the sort of stuff I want to show you happens. All right? It's just that, the velocity of the shock is going to be different from the one I'm using here. But I don't know what that law should be. Okay? It clearly is related to the fact that cars are braking near the shock, and that's how you get this sharp transition. But the stuff that's conserved, I guess, is the life of the drivers, and I don't have a mathematical expression for that one. All right. So I'm going to show you now some numerical calculations. This is just numerics. We're taking the circular road with 500 meters. That's kind of roughly the length of that Japanese thing. But instead of having 22 cars, I have 9. So the density is lower. Okay? And if you now look at what happens.
So how do you translate your continuing equation to 9 cars?
You just look at the density. Okay, the density is cars per length. So if I have 9 cars in 500 meters, then I have 5 cars, 18 cars per kilometer. That's my density.
And how do you compute the gradient of the density?
Is a constant. Rho is a constant. Rho is a constant which has the value 18 cars per kilometer. That's my initial data.
Still continuous.
Is it continuous?
He's just assigning arbitrarily number 9.
Right. I mean, when I design the density, what I'm saying here, the density here is 18 cars per kilometer. That is the value of rho. It's a constant. So that corresponds to 9 cars in a 500 road circular road.
I'm confused because it said on the last slide it's a Lagrangian method.
That's the numerical method. You can have particles. The particles are numerical particles. They are not cars. Okay? Sorry about that. Yeah, that's... All right, so you start this thing. And this one is... I'm doing the Pine-Witten one. It's boring. Okay, nothing happens. I mean, the velocity here is the one that corresponds, is the one that the drivers want to be at when that's the density. All right? And, nothing happens. The guys drive around the circle, and they do what they were instructed to do. Well, okay. Not really. Okay, let's now go to the next case. Now I want to take the same road, but instead of 9, I'm going to put 18. Same constant, higher.
Is it perturbation
Well, the perturbations, it is an instability. I mean, you put obviously the exact solution is 18, but it's like you telling me, okay, this wave is if you have an unstable wave, there are always going to be instabilities around. I mean, little perturbations. Anything like a driver sniffed a driver coughed or in my code we put a little tiny thing. Okay, you can see it there. Yeah, a very small. Oh, yeah, of course we put a perturbation. If we don't put a perturbation, you have to wait for the numerical perturbations to do it. Okay, and it takes longer. But it happens anyway. All right? Huh? I can't shoot the laser at you. What are you saying?
9 drivers sneezed at the same time.
No, well, in this case, yes. And so what happens now is you wait and you see that, I think, okay. All right? Well, the cars, I'm doing the same thing that John did. Jesus. I have the solution. Now I put cars and I solve the equation x dot equal to u, and I just plot them.
It just means twice the density.
Yes. I thought you were asking about the cars down here. If you actually look, these are cars, okay? Okay, and this is the same trick that John did this morning.
How do you get MATLAB to plot cars?
Okay.
That's a different topic.
You have OCD collaborators that spend days plotting, okay? All right. So, okay, this restarted now, but the point is you get this stuff happening. All right? And so basically, if you look at the model and you just go in and you analyze the constant state, you find out that it's possible to get it unstable. All right? And you go through the calculation, and you know that the condition for stability is this one here. This is the one using the pressure, which is beta rho square. Okay? And in that case, the instability happens to be given by this. The parameters are rho m, which is the maximum density at which cars stop, and this beta, which is the kind of like a measure of how preventive the driving is. The larger the beta is, the more cautious the driver are. And um, which is kind of like the speed limit, basically. All right? And so if the density is below this number, then it's stable. If you go above it, it's unstable. All right? So 9 was below, 18 was above. All right? And so, okay, so now, I want to tell you about, so I want to show you now what these waves, so these instabilities appear, they have start growing, okay, and they become nonlinear, and they sort of saturate into these waves you saw that, which have this high spike there. So the issue is, what are these waves, okay, in which they saturate? And essentially what I'm claiming is these are detonation waves in traffic flow. All right, the same theory as detonation waves. So let me just tell you what the theory is. All right, so this is the traffic flow version of the Celovich-Neumann-Dorin theory of detonation waves. The detonation wave consists of basically, first, there is a shock wave, here it is, that moves into the media, triggers a chemical reaction. There's a reaction zone behind the detonation wave till it hits a place which is sonic point. At the sonic point, the velocity of the detonation wave is equal to the characteristic speed. The characteristic speed here are these two guys, all right? That's one of them, and that's the other one. And this is the shock speed. Ahead of the shock, both characteristics are going into the shock. Behind the shock, one of them is going into the shock, the other one is crossing. And then there's a point at which they line up, and then both of these guys are moving away from the shock. So that means that this place here is isolated from the rest of the fluid. In other words, you cannot get information from here going into here. Okay, so this guy becomes now independent of the flow behind. Okay, and that's why the detonation can just move without any external supply of anything. It just goes. And the same thing happens here. Instead of having a chemical reaction, what this is the car engines. All right, there's a supply of energy that the drivers have at their supply that they use to accelerate. Okay, and that's essentially the equivalent of the detonation wave. Unlike gas dynamics, when once you use the the chemical reactant, then you're done. In this case, the engine keeps on running, so in fact you can have trains of these things. Not just one, but many. One behind the other, or for that matter, you can have a periodic one going around and around through the same media. Okay? But the idea is the same. All right? And so the sonic point means just that the speed of sound, which in this case, this one is the one moving to the left. So this shock corresponds to the left characteristic, which is u minus c, u being the velocity and c the speed of sound or whatever. It's not sound in this case, all right? It's the speed of, I don't know what to call it, but whatever, equal to the shock speed, all right? So that's the structure. And so I want to show you now that such waves do exist in the context of these models, all right? Well, I'm not going to show that. I'm just going to claim it, and it's a bunch of algebra, all right? But basically, the idea is that the key thing is that you have the shock, and then you have the smooth part, which is this one, and you just have to show that you can connect them. In other words, I can get the smooth part that will connect this guy to the next guy, in the case of the periodic case. And so that means that you just have you plug in this formula for the solution, and then you get an ODE, and now you have to show that ODE has the correct solutions. And the main difficulty is related to the fact that because the shock satisfies these entropy conditions, somewhere in between the two values on the shock, right and left, the sound speed is sonic. So your ODE has a singular coefficient. And you have to make sure that the two coefficients, that the coefficients vanish in such a way that you can cancel out the zero so the solution can go through. Okay? And that's the sonic point. That's the only part that's quote hard. It's not really hard. All right, in any event, then you can show the following thing, that you can do this thing provided there exists a linearly unstable state, okay? And it turns out that linearly unstable state is precisely the sonic point or event horizon. All right? So given that you have that, you can produce them, okay? And they're basically a two-parameter family of solutions, all right? I mean, one parameter family one parameter is the velocity, and the other parameter is the amplitude of the shock. Okay? So I have a ton of these guys. Another way of parameterizing them is you can parameterize them by the period, if in the case of periodic guys, and the mean value. So now what I'm going to show you now is like I give initial conditions, I look at the initial conditions, I look at the period and the mean value, that identifies one guy, and what happens is the solution goes to that guy. So these guys are not only exist, they are actually attractors. That's where the system wants to go. All right? So we decided to call these guys jammetons, and the reason is that they look like particles in the sense they're independent of the once they form, they become self-sustaining, they just move through, okay? And they have various properties. They always move backwards on the stream of traffic, okay? So the cars always are hit by the shock first, and then they go through the back part. They can, relative to the road, they can move in either left or right, but relative to the cars, they're always moving against the cars. The other point, there are two interesting. One interesting point is this one here. At the spike, the car density is quite high, and if you look at the car movie I showed you, you can see that. Right there, the cars get very close together. So these guys are kind of like hotspots for accidents. I mean, that's the place where an accident is going to happen, if it's going to happen at all. So they're bad guys. You don't want them. They also involve a lot of acceleration, which means increased fuel consumption, more pollution. So these guys are really the bad guys in the fairy tale. All right. So you want to get rid of them. So it would be nice to know how to get rid of them. I don't know how to do that. Okay. So let me show you some calculations. All right. So this one, so again, it's a circular roll. I'm starting with some initial conditions, which is a small perturbation of a constant state. For this constant state and that particular mean value, there is actually a jammeton that you can calculate theoretically. Just go and solve the ODE, all right? And this is what happens. The theory will pop up in a moment. That's the theoretically computed one. That's the yellow one. And that's what the evolution looks like. Okay, and it goes to it. All right? The colleague of mine that did the plot claims that these guys are actually Volkswagen Golfs. He's a German guy. Okay.
What determines the period of shock?
Oh, in this case, we're just putting it in the initial conditions. Okay, so I'm doing a circular road, so that's it. Okay, I mean, there are situations where, for example, if I were to put the same initial conditions I put here, but on a road twice the period, well, I would get two of these guys inside. All right? So, all right, this is now, why not show you pretty pictures? This is the same calculation now, but illustrated from the point of view of a viewer outside.
You forgot to pass us a remote control.
What?
To play it as a
Oh, right. Okay.
Is this a real discrete model simulation?
This is the same simulation that I showed you a moment ago, in which we just put the cars there and we solve the, again, the same trick as John. Once I know the solution, I can put cars and follow them. Okay? All right. So okay, I'm not going to, let me keep this one. Okay, I'll just tell you what this is. All right, I mean, these models are, of course, kind of like crappy, honestly. All right, and so there are also effects that are neglected. So one thing we decided to do, how stable is this stuff to small perturbations, like, for example, put some viscosity into them, all right? I don't know what this viscosity is. People actually in traffic flow write these things. I don't know why they write them. It's not clear how to justify them. But we decided, since these guys write that thing, how bad is this going to change it, all right? And it doesn't, all right? As long as this thing is small enough, you look at the calculation, and it's just the same answer, slightly perturbed, all right? So it's a pretty robust thing. I'm not going to show you the pictures for that one. So. All right, now here is your infinite road thing. So in this one, we're actually taking a very long road, okay? And we go to one of these unstable states. The road is much, much longer than any periodic thing, so we're not going to get periodic things. But this is what happens. I think that's what this is. All right, so this guy here is the theoretical one. So you see that the solution evolves towards this one. Okay? But something happens. A second one is formed on the back of this guy at some distance away.
What sets the shock width?
Oh, this is implicit. Okay, so.
I know, but I mean, there's.
Okay, hold on. Let me.
You
You mean this?
Yeah.
Oh, that's the solution of the ODE. Look at the yellow line, which is now underneath the.
But there's some set of parameters that are combining to give you some sort of length scale there.
Well, I have an average, and I'm all right. In this case,
because the ones that are further down seem a little narrower.
Yes, we don't actually know what is set in the various parameters. No, we don't know that. Okay. In other words, these guys have two parameters. Okay, and the average value we gave to the initial conditions, that picks one of them. What picks the other one, it's not clear. All right? Perhaps, it might actually be that the wavelength that's the largest in your perturbation is the one that dominates initially, but then you get all these trailing ones, which are produced by, I don't know what, we call them jamitinos.
How do you decide on the second parameter for the yellow curve?
Well, that one was fitted. Okay, once we know the amplitude, we want to see how, it's an extra parameter like the shock height, and given the shock height, what would be the rest of the flow, and it's the right one. Okay, but we don't know how to get it. All right. Okay, but the RI is an infinite roads also. You don't need a periodic road. Okay, so I think that's probably. Oh, this is because why it's not moving? I think this is because we're just moving the computation with the shock. Okay. Or is it moving? I don't know. These guys can move forward or backwards, all right? It's a question of what is the shock strength and what is the state ahead. relative to the road. Can the what speed? Okay, there's one parameter I don't know how to predict. Okay, now there are two parameters that characterize this wave. Okay, and I know one of them, which is the average value of the density. I don't know how to predict the other one. In the case of a periodic road, I can, because I can pick the period as the other parameter. When there is no period, I don't know how to pick it. And of course, that means I don't know how to pick this. This gives you a train of progress one next to the other. You know, what sets this separation, what sets this amplitude, I don't know. That we don't know. Okay?
Can shock speed be predicted according to the shock strength, namely the...
Yeah, well, that's the shock law that relates the jump to the velocity. Yeah. I mean, that was the point I made before. These shocks are being computed assuming conservation of cars and conservation of momentum. Now, that's wrong. Cars are conserved, but momentum should not be conserved. So again, what should be the actual true thing that you use to complement conservation of mass? It's not known. Okay? There's no way to actually do that in a rational way. So these shocks are wrong. Okay. So this is the last one, and this is when my, this is the same calculation which you saw before, but seen animated with cars, okay, and it's happening on the desert, in the Mojave Desert, and there's a marine helicopter following the cars, something like that. I mean, I don't remember what the story was, but I mean, okay. It's supposed to try to mimic what you see in the Cairo Road. All right, anyway, okay. So, there's a whole bunch of questions.
Same kind of camera work, actually.
Huh?
It's the same kind of camera work, actually.
Huh?
It's the same kind of camera work, this constant kind of zooming back.
Yeah, well, it's the same guy that did it. Okay, I think this is either, I think this was done by Jean-Christophe Nave. Okay, so it's a French camera. So there are a whole bunch of things we don't know the answer to. One of them, for example, is the question. The fundamental question is what determines the shock speed? The real thing. It's not conservation of momentum. It's something else. Okay, we don't know. All right. We're not the only one that don't know. In fact, in the traffic flow community, this has been a thing that's been around since for like 20 years. People have been discussing what to do. So that's one. Second one is, even if I know that, all right, like in the open road, what determines the size of this guy? Okay, I don't know. Second question, more important, is what happens if you have a two-lane road? All right, and now you have the cars can exchange. Okay. Well, we have done some numerical experiment with two-lane roads. The first problem, of course, is there are no good models for two-lane roads. But, picking some models that are as good as we can make them, all right? You can do some experiments, and we're doing them now. It's not clear what happens. I mean, sometimes these guys seem to lock together, and so you get two of them on the same, locked together in the two lanes, and sometimes they ignore them, okay? And so you have one on one road, on one lane, and the other one is not there. I'm not sure. I don't know whether this is just defects of the model or what. Okay, I mean, if you actually look at roads, you see both. Sometimes you see that the two lanes are being blocked, and sometimes you see that one lane is blocked and the other is not. So these things happen. All right, but in terms of the models, we don't know what's causing that. Okay. The third point is how are these guys affected by traffic conditions? Not traffic conditions, by external parameters. For example, imagine you have the road, and every 200 meters you have a billboard, all right, showing something, some message that says you're an idiot or whatever. Okay, how would that affect these guys? Can you use such things to, maybe make them less likely or something like that? So again, we think that would affect them, but we are studying it. Okay, and that's it. I think that's it. No? God, I'm stuck. Okay, so that's the end of the trial.